So again, we've extensively covered sine and cosine, but obviously most of you have had experience with trigonometry before class, and so you're probably thinking, well, what about the other ones? How do we tackle the other items? And so I have that same circle from a previous lesson that has cosine representing our x values and sine representing our y values. So for any point xy on a circle of radius r at an angle of specifically theta, we now are able to define all 6 important functions as ratios of sides of the corresponding triangle. So we've already talked about sine is the y value over the radius. We also talked about cosine being the x value over the radius. Now we're going to define tangent as our y value over our x value. Well, our y value over our x value. So recall that we could define x as the radius times cosine of theta, and y is the radius times sine of theta. So if I'm defining tangent as y over x, that would be the same as radius times sine of theta over radius times cosine of theta, where the radiuses would just end up eliminating, so then all I'm left with is sine over cosine. And this is going to be one of the major ones that we're going to utilize quite frequently to replace, so keep this guy handy. And I did mention it when we were talking about our unit circle, but this is kind of a more formal definition. All right, secant is SEC with our theta is the radius over the x value. So secant and cosine are the opposites of one another, or reciprocals of one another, I should say. And cosecant then is the reciprocal of sine, since we'll have the radius over the y value. And then tangent and cotangent are also reciprocals of one another. So here are some important identities that we're going to need that are all related and can be written in sine and cosine. Once we start transforming and simplifying trig functions, it'll be important for us to be able to write things in sine and cosine, as it is much easier for us to simplify items. So I've already stated above that tangent is sine of theta over cosine of theta. Secant, since it's the reciprocal of cosine, I can write secant as 1 over cosine. Cosecant is the reciprocal of sine, so 1 over sine. And then cotangent obviously is the reciprocal of tangent, so just cosine over sine. And many of these are all listed under your basic identities on the top left-hand corner. Of your trig identity sheet. So all of these are listed on the top left-hand corner, so you don't have to memorize them or convert them. They're already on there for us. So then let's head to page 2 and do some evaluating. Tangent of 45 degrees, and also find secant of 5 pi over 6. So 45 degrees is one of those nice values for us. We'll also see that on our exact trig value chart that tangent does exist, because sine, cosine, and tangent are those that are frequently utilized. But we'll do it the old-fashioned way so we can see, how does it become 1? How is tangent of 45 degrees 1? So I'm going to start with tangent of 45 degrees. I know tangent is the same as saying sine of 45 degrees over cosine of 45 degrees. And now looking at our chart, or looking at your unit circle, sine of 45 degrees is square root 2 over 2. And cosine of 45 degrees we also know is square root 2 over 2 because their sides are equivalent, and anything divided by itself is 1. So that's how on our exact trig values on our sheet, when I look at the 45 degree row and shoot all the way over, I see tangent of 45 degrees is equal to 1, and this is why. When I'm thinking about secant of 5 pi over 6, we don't have secant on our sheet, right? We only have sine, cosine, and tangent. Even with our unit circle, we only talked about sine and cosine. But I do know that secant is the reciprocal of cosine. So 1 over cosine of 5 pi over 6. And we could utilize our unit circle. I know that cosine of 5 pi over 6, since cosine represents our x value, I know that I'm going to be in either the second or the third quadrant where cosine is negative, and it's directly related to pi over 6 or the 30-degree value. So I know I need to take this as 1 over negative, because cosine of 5 pi over 6 is in the second or third quadrant, square root 3 over 2. Now I'm dividing by another fraction, so I've got myself a complex fraction. So as a reminder, I can multiply by the reciprocal. So 1 times the reciprocal. This simplifies to negative 2 over square root 3, but we have to rationalize that denominator. So I'm going to multiply the numerator by square root 3 and the denominator by square root 3. Therefore, I have at negative 2 square root 3 over the square root of 9, which then simplifies to negative 2 square root 3 all over 3, since I know the square root of 9 is 3. And we were able to rationalize the denominator. All right, let's then evaluate cosecant of 7 pi over 6. And then think about using the related triangle that we talked about in our last lesson. So here, this previous one using secant, I used my unit circle. Now I'm going to use a related triangle to help us instead, just so you can see both of those options. Some of us relate with one over the other. So I'm looking for cosecant of 7 pi over 6. So I know 7 pi over 6, if I were to start at my initial angle, it's going to be about here-ish, right? We drop our vertical line down to the x-axis. So I know my x value and my y value are going to both be negative. But if this whole thing is 7 pi over 6, I can find my related triangle by saying 7 pi over 6, subtract pi, because this is pi. So this part is pi over 6. So I can look at pi over 6 in my radians or a 30-degree triangle to help me identify what this might be, knowing that we are in the third quadrant, so both the x and the y values have to be negative. So I'm using that reference triangle to help us out here. So I'm going to start with cosecant of 7 pi over 6. I know that this is the same thing as saying 1 over sine of pi over 6. Again, using the reference triangle. However, because I know I'm in the third quadrant, I know that whatever this is has to be negative. Thinking about the sign in which we're in, where are we located? Now I can rely strictly on my exact trig values instead of having to pull out my unit circle every single time. So pi over 6 for sine is half, but I know it has to be negative half because we are in that third quadrant. And again, 1 multiplied by the reciprocal gives me negative 2. So again, you can either use the unit circle like we did here, just to kind of look around the circle, or you can use the reference triangles like we did in example 2. Doesn't matter to us. All right, so let's focus on simplifying trig values. This is my favorite part. It's like a puzzle. Give yourself some grace when you do work on these. Sometimes you're going to start and it's not going to turn out the way you want. And it can be frustrating. Sometimes we'll start on the left side and work our way. Sometimes we'll start on the right side and work our way. But we're just asked to simplify. And it might look simplified to you right now, that secant over tangent is just 2 different trig identities. However, we can simplify this down. Notice that we're in secant and tangent. My hint to you sometimes is to turn our items into sine and cosine. Because sometimes we'll be able to eliminate some items by turning it into sine and cosine. So I know secant is the reciprocal of cosine. So that's the same as 1 over cosine of theta all over. And I know tangent is sine over cosine. I've created myself a nice complex fraction where we can multiply by the reciprocal. And you'll notice what happens when we do that. You'll also notice they have the same denominator, so there's 2 different ways you could approach it. But I notice that I have something, a factor in my numerator and my denominator that we're able to eliminate. So all I'm left with is 1 over sine. And 1 over sine simplifies to cosecant. So what we've just discovered is that secant over tangent is equal to cosecant. So we created a new identity. Pretty cool. It's not a popular new identity by any means, but what we did is found a new identity. So it's not going to be written on our identity sheet because it's not one that you're frequently going to need or come across. Sometimes it'll ask you to prove the identity. So prove the identity that 1 plus cotangent over cosecant. Prove that it is in fact equal to sine plus cosine. Now, you can either start on the left and make it equal to the one on the right, or start on the right and make your way equivalent to the one on the left. I'm going to start on the left-hand side just because all on the right-hand side I have a sine plus cosine, and I would have to be pretty clever in order to make cotangent and cosecant. But using my hint above, by turning items into sine and cosine, I might be able to more easily find the right-hand side. So I'm going to start on the left-hand side, and I'm going to turn all of my cotangents and cosecants into sine and cosine and see what might happen when we do that. So this will be 1 plus cotangent. Cotangent, looking at our trig identity, is the reciprocal of tangent. So I'll have cosine of alpha over sine of alpha all over. Cosecant, I know, is the reciprocal of sine. So 1 over sine of alpha. Again, we have this complex fraction. I'm going to rewrite it as multiplying by the reciprocal. So 1 plus cosine of alpha over sine of alpha times sine of alpha, and I don't need to write it over 1. But right now I've got this binomial times a monomial, so I'm going to multiply this through and see what might happen to eliminate our parentheses. This will then give me sine of alpha plus sine of alpha times cosine of alpha all over sine of alpha. We notice in the right-hand side that there is a common factor in the numerator and denominator that can be eliminated. And thus, we have sine of alpha plus cosine of alpha, alpha not theta, which is exactly what we wanted to equal. So now we know we're done. We found that the yes, in fact, are equal to one another. So that tells me that we are over. All right, example 5 on page 4. Here we're going to establish an identity. Establishing an identity is the exact same thing as proving the left equals the right, just in different verbiage. I notice here on my numerator that I have cosine squared, and in my denominator I have 1 plus sine. So everything right now is already in sines and cosines. However, I noticed that in my numerator I have cosine squared, and we decided that this was a Pythagorean identity from sine squared plus cosine squared. So I'm going to use the Pythagorean identity. So I just pulled this identity straight from the top portion of our Pythagorean identities on the top right of our trig sheet. I also see that the third one down, if I were to get cosine squared by itself, that's the same as saying 1 minus sine squared of theta, by just simply getting rid of the sine and bringing it to the right-hand side. That's all we did. So that's where I'm going to start, because then at least I have a sine in my numerator and denominator, and I've gotten rid of my cosine. So I'm looking and trying to get to the right-hand side here. So I'm going to replace cosine squared with 1 minus sine squared of theta over 1 plus sine of theta. Well, I cannot just simply notice that they are separated with an addition and subtraction, so they are not in multiplication. So I am not able to just eliminate whatever the heck I want, because they are connected with an addition and a subtraction sign. So I need to use a difference of perfect squares in my numerator. So I'm going to factor All right, so we're going to use a difference of perfect squares to factor this. If you need a reminder, let's just replace sine with x. So if I had 1 minus x squared, this factored form would be 1 plus x, 1 minus x, right? So if I were to distribute, I would have 1 plus x minus x squared. The x's would eliminate, so I'd be left with 1 minus x squared. So that's kind of the generic version. So I can do the same thing. All I need to do is replace my x's here with our sine value. So we can still factor just as we would with regular x values. This is then the same as 1 plus sine of theta times 1 minus sine of theta, all over 1 plus sine of theta. Now we are able to eliminate because we have a binomial times a binomial. So we have a complete factor in the numerator and a complete factor in our denominator, leaving us with 1 minus sine of theta, which again is equal to the right-hand side. That was our goal. So we know we are done. We know that this is a good combination. And we established a new identity. Again, not one commonly used, but it's there. Let's establish that cotangent squared is plus 1 is equal to cosecant. And you'll notice that this is an identity on our Pythagorean identity side, with the cotangent plus 1 equal to cosecant. So let's see how we can actually get there. So I'm going to start. I noticed that I've got some cotangent here. I'm going to turn this into sine and cosine so that you can see that even with a square, I can still turn it into sine and cosine. I'm going to be a little creative here. I know cotangent is the reciprocal of tangent. So it's going to be cosine squared of theta over sine squared of theta. So notice that that square follows it. So far, plus 1. Then I'm going to use the Pythagorean identity for my numerator. See what might happen. The same identity that we worked with on the last example. So my numerator will now be 1 minus sine squared of theta over, plus 1 over here sine squared of theta. What I'm going to do now is decompose my numerator and break apart that fraction. I know that this fraction is equivalent to 1 over sine squared of theta minus sine squared of theta over sine squared of theta plus 1. Well, then what happens in our middle here is that they're the same item, so we're able to eliminate them. I just have 1 over sine squared of theta minus 1 plus 1. So when they're eliminated, we have a 1 here because it reduces. So that when I add these values, they also create a 0 pair. All I'm left with is 1 over sine squared. And I know the reciprocal of 1 over sine is cosecant, so this is the same as cosecant of theta, which is exactly what we wanted to come across up here. So this is another Pythagorean identity. This is on our Pythagorean identity sheet, 1 plus cotangent is equal to cosecant. And then all of the other options that are listed there by adding and subtracting, just like we did the previous ones. I also give you another one that 1 plus tangent squared is equal to secant squared. And then, of course, adding and subtracting as needed to find the other items. All right, a couple more examples, and we are near the end. Tangent is equal to 2/7, and theta is in the third quadrant. Let's find cosine. I'm going to show you 2 different ways we can reach that. I'm going to start us off with a visual effect, a visual model first, which I think you'll like. So I know I'm in the third quadrant. We don't know what the radius is. I know that tangent is y over x. And I know since I'm in the third quadrant that both my x and my y have to be negative. So I have to go -7 units to the left and -2 units to the down. But in order to find cosine, right, I need cosine of our value. In order to find cosine, I need our x value over the y value. And right now, all I have is the x value. We don't know what our radius is yet. So we need to obviously use Pythagorean's identity, or excuse me, Pythagorean's theorem with our right triangle, so that I have -7 squared plus -2 squared is r squared. 49 plus 4 is r squared. 53 is r squared. So our radius has to be the square root of 53. Our radius is always positive, so it doesn't matter what our value with respect to that is. Okay, so going back to cosine then, cosine of theta then has to be -7 over the square root of 53. But again, we don't like to have the radical in the denominator, so we will rationalize that denominator by multiplying by the square root of 53. -7 square roots of 53 is also 53 on the bottom, because we'll have the square root of 53 squared, which simplifies. So we found that in a few short steps. The second approach is using Pythagorean's identity from the previous page. So we're going to use a more a non-visual approach, an abstract, I should say. Abstract might be the better way to do that, using Pythagorean identity. And the one I'm specifically going to utilize, because I know secant is the reciprocal of cosine, and cosine is what we need, I'm going to utilize 1 plus tangent, because tangent is what we have, of theta equal to secant squared of theta. I know that tangent is 2/7, so 1 plus 2/7 squared equals secant squared, or 1 plus 4/49 equals secant squared. Combining our fractions, we have 49/49 is the same as 1. So 49/49 plus 4/49 doesn't surprise us that we have 53/49, because we know we're going to end up with 53 somewhere, equal to secant squared of theta. When I take the square root to undo, we will have plus or minus the square root of 53 over 7 equal to secant. Since we know we're in the third quadrant, we know our cosine is negative in the third quadrant. So I'm only going to be curious about the negative version. Therefore, since I know secant is the reciprocal of cosine, I can say then that 1 over cosine is equal to negative square root 53/7, or cosine then is equal to the reciprocal -7 over square root 53. But then rationalizing that denominator ends up with -7 square root 53 over 53. So we ended up with the same solution. we still had to think about what the third quadrant meant with respect to the positive or negative version. I will never ask you to do one way over the other. Sometimes we need to use Pythagorean's identity, and other times using the visual representation is just fine. So keep that in mind. And our last example, actually throwing in some radians here. So if secant of beta is -7/3 and our beta is in between pi over 2 and pi, find tangent and find sine. I'm going to use the visual model since many of us, I suspect, are visual. However, you could also use Pythagorean's identity. I don't think we'll have time to do all of the Pythagorean identity, so we'll just focus on the visual version here. Well, if I think about in radians, where is pi over 2 and pi? Pi over 2 to pi is in the second quadrant. So we're going to be over here somewhere. We know that secant is -7/3. So secant is the reciprocal of cosine. So 1 over cosine of beta is also -7/3. So if we write their reciprocals, cosine of beta has to be -3/7. We know cosine is our x value over the radius. So the negative belongs to 3. We're in the second quadrant, drop down our item. So -3 over our radius. We definitely are going to need our y value since I need tangent and sine. So let's find that y value by using Pythagorean's theorem. So -3 squared plus y squared is 7 squared. 9 plus y squared is 49. Y squared is 40. Y is equal to plus or minus the square root of 40. I know 40 is the same as 4 times 10, and I can take the square root of 4, so plus or minus 2 square roots 10. Now, because we're in the second quadrant, our y value is positive, so we can ignore the negative version. And now we have our x, our y, and our radius. Therefore, we can find tangent and we can find sine. Let's start with finding sine. So sine of beta. Our sine of beta is equal to our y value over the radius. So 2 square root 10 over 7. And that's completely simplified. Also, from our front page, we see that tangent of beta, you could either say it's sine over cosine and then reduce it, but we also know that tangent is the same thing as saying our y value over the x value. So 2 square root 10 over -3, which reduces to -2, just putting that negative either on the top or the bottom, -2 square root 10 over 3. So I like that these have a lot of different options with respect to being able to solve. So just kind of take it with whatever you see first. Don't try to do all of the different ways at once. Just go with what you see and what makes the most sense to you. I'll never ask you to do one way over the other. I'd rather give you multiple options and then you get to pick which option that you like the best.